Okay, we had last time computed the partition. We had last time computed the partition function of the 26 bosons, and we had got this. We had got 1 over tau 2 imaginary tau to the power 13. We had got 1 over that. Then we had got 1 over eta tau mod square to the power 26. That's right? And this by itself was modular invariant using the relation that square root im tau times mod eta tau square is modular invariant. Please check if I'm reporting something wrong. Please check from your notes. We'd also computed, this is X, and then we'd also computed ghost, so BC. And we had got, I'll report, we did something wrong last time, I'll correct it. But what had we actually got? We had got, I think we reported that we got Q bar times times eta tau squared square. Is this what we said last time? Times, yeah, I think this is what we said last time, right? This was, of course, was wrong, because it would not have been modular invariant. And the reason for that was very simple, very stupid of me. This came from the, let me remind you what we said. We said that the zero mode contribution was Q bar to the power 26 by 24. Where we were using that the zero mode contribution, we were using that the 0 point energy was Q bar to the power minus C divided by 24, and using the fact that C for the ghost system was minus 26. But remember what this is the right formula for. This is the formula for the state dual to the identity operator. Remember, where did we get that formula? We got the formula by the conformal transformation from the plane to the cylinder. Using the fact that the identity operator has dimension 0, then for that, the state corresponding to that operator comes entirely from the conformal transformation, the Schwarzian part, and that gave this contribution. But let us remember that in the BC system, the state corresponding to the identity operator was not the vacuum. In fact, the vacuum was the state corresponding to the operator C. And that had an additional contribution, additional energy contribution minus 1. So there's an extra factor of Q to the power minus 1, Q bar to the power minus 1. Because we started all our, we assumed that the ground state had energy 0, right? Actually, we should have said the ground state had energy minus 1 in addition to this factor, and that cancels this additional Q bar. Okay, so that Q bar was a silly mistake in the 0 point energy. Okay, clear? Okay, so now that we've got this, we've got a nice modular invariant answer separately for the ghosts and the matter. And what remains is now to integrate over the torus, over the moduli of the torus. So we want to do d2 tau divided by im tau times the product of these two things. Okay. Now, in the product of these two things, this cancels two of these factors. So we've got 1 over im tau to the power 13 times 1 over eta tau mod squared to the power 24. Right? Now, now Now, the fact that we've got this extra factor, you see, 12 of these go into here, are naturally paired with this, and the 13th one comes here. And the reason this is nice, is that this quantity by itself is a modular invariant measure. Okay, so let's check that. For instance, under tau goes to 1 by tau. Okay, so suppose tau goes to minus 1 by tau. Okay, so then d tau is equal to d tau goes to, okay, let's do it properly. Let's say tau is equal to, then d tau is equal to minus 1 by tau prime squared, d tau prime.
No, just plus.
Plus, thank you. Plus d tau prime, and so d tau bar is d tau bar times tau prime mod squared, mod to the 4. Okay. On the other hand, let's look at how im tau scales. Okay. So suppose tau was equal to tau 1 plus, we did it, right? Yeah. Wait. Anyway, tau 1 prime plus tau 2 prime.
That will cancel all of this.
It cancels this. Mod tau square, right? So it cancels this. So now the whole thing is now beautifully modular invariant. This is modular invariant. This is invariant by itself, and we've landed on our feet. So we've got a good answer. Okay, we've got a good answer, and now we're going to study the answer. We're going to try to extract some physics from the answer. Any questions or comments about this? Okay, great. So the first question that we're going to ask is, over what is the range of integration? What is the range of integration? Okay. What is the range of integration of this tau parameter? Okay. So now, what is tau? Tau is some complex number. Tau is some complex number.
What is to begin with in the upper half plane?
Yeah, right. So some complex number. Let's say in the upper half plane, if we choose that. The torus is identified this way rather than that way. Clearly, you can always choose that. Okay. Now, so some complex number here. But if I take tau goes to tau plus 1, I clearly generate the same torus. Because our definition of tau was that z was the same as z plus 2 pi.
Yeah,
And z was also the same as z plus 2 pi I tau. 2 pi tau, thank you. 2 pi tau. Therefore, if tau is tau plus 1, this identification is the same as this identification. Because once we know that this is the case, it's also true that z is identified with z plus 2 pi m plus n tau. You just repeat the identification. Okay? So tau we should think of this way. Tau generates a lattice. Okay? We should think of the complex tau plane as with the two generators, this 2 pi and tau, as creating a lattice. The lattice is the set of points that we get by acting repeatedly with these translations. Okay, so for instance, you go here, 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 here. Then this guy can go here, 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 here. I'm not very good at drawing this. Sorry. You should always all of them the same. And then this guy is here, 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 and so on.
So basically m comma n.
M comma n. Right? So you see you're getting the whole lattice. Now, suppose somebody else gave you the same complex plane and said, no, 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 my generators are this, because by convention we always choose that, and this. Clearly you're getting the same lattice. Okay? More generally, any tau goes to
just the real direction, that's
exactly.
real combination.
Tau goes to tau plus m is clearly also generating the same lattice. But there is one more thing. Okay? And the other thing is that if we can get back, see, in this metric, in this space, our metric was dz bar. Okay? But suppose we do some sort of transformation such that the metric changes not, doesn't remain, this transformation, you know, this z goes to 2 pi and z goes to z, tau and tau plus 1, they're basically related by some sort of z goes to z plus constant. But you see, now if I do the following, I can also do the following. I can also change what my z is so that this becomes the imaginary direction. I mean, this becomes the tau direction, and this becomes the real direction.
After some
rotation, basically.
Or maybe a rotation and a deflection.
Yeah. Okay? That can also describe the same lattice. That is basically generated by this tau goes to 1 by tau, minus 1 by tau. Okay? For instance, suppose this was along the real axis. Okay? Suppose this was along the real axis. Then what are we getting? What we are getting is this guy has length 2 pi and this guy has length tau 2.
But now the angle is along that. I mean, you have rotated the lattice, right?
I've not yet done it.
Okay.
Suppose this is what we had to start
Yes.
with. 2 pi and 2 pi tau. 2 pi tau. Now, if we do what happens if we do tau goes to 1 by tau? Tau goes to 1 by tau takes it to the identification 2 pi and 2 pi by tau 2. Actually, minus 1 by tau, because I minus inverse of I would be minus. So that's the reason for the minus. So to keep the upper half plane, keep it always in the upper half plane. Otherwise, if tau goes to 1 by tau, would have taken the lower half plane. Okay? So this looks like a different identification. This big guy has shrunk to the small guy. But now, let me imagine that this is my x-axis and this is my y-axis. So now what do I have? I've got the identification where this guy is tau 2 times 2 pi. And this guy is 2 pi. Now suppose I do a scaling of the z coordinate. I scale it to make this length
1.
Sorry, and this was now 1 by 2, 1 by tau 2.
Yeah.
Okay? So now suppose I do this and I scale z to make this 1. That will become 2 pi times tau 2.
Yes.
Okay? And that's the original torus. Okay? You can easily convince yourself more generally that tau goes to minus 1 by tau gives you the same torus, just that you have to use a different z coordinate. And it gives you the same torus with a metric that is not the same. That's like a scaling, but a metric that is the same up to a constant overall factor. But we're only interested in things up to Weyl transformations, constant overall factors, and no sweat for us. Okay, so we just throw them away. Okay, so our tori here, our tau is not to be thought of as a vector. It is to be thought of as a vector modulo these transformations. That any two taus that are related by either tau goes to minus 1 by tau or tau goes to tau plus 1 are to be regarded as the same torus. But you know, now when you've got two operations, you can try to do one after the other. You can first do tau goes to tau plus 1 and then do tau goes to minus 1 by tau, and then you get something that's neither one of these. So what you have to do is to look at the whole group generated by these two operations. And it is not difficult to convince yourself that this group is tau, is the group generated by tau prime is equal to a tau, sorry, m tau plus n m tau plus n over p tau plus q. Okay, where everything is an integer, and more precisely, you know, if we choose,
determinant is 1.
That's right. So exactly. So m n p q, such like the determinant is equal to 1. This is called SL 2Z. SL tells you that its determinant is 1, and Z tells you that the elements are integers. And I think there is a Z2. Yes, exactly.
Because of all the whole inverse.
Because if you take m to minus all of the integers to minus themselves, you've not changed the right hand side at all. So not all of SL2Z is acting on this. You know, only up to a modded out by Z2. So SL2Z mod Z2, all that. Okay. Yeah. Okay. So these transformations, the transformations generated by these are given by this group, and we should only regard the tori as different. Okay. If they cannot be related by an if the two taus that can be related by an SL2Z transformation, okay, are actually the same tau. So now a question we're going to ask is, when we do the integral over all tau, if we just actually do the integral over everything, we will just get infinity. Because every time we're doing the, you know, we will have a copy of the volume of SL2Z. Volume of SL2Z is just number of points in SL2Z, but that's infinite. Right? Because you get the same two tori that are related to each other by SL2Z, give you the same answer because it's the same torus. We've been very careful to see that the whole answer is modular invariant. So you'll get the same answer. So then it's like doing the integral only over one copy, one fundamental domain times infinity. So clearly we're supposed to mod out by infinite by these things. Now what was from the point of view of our derivation of the things in string theory, what was the rationale for modding out? Well, we were very careful to mod out by diffeomorphisms. But you know, if you think back, what we did was mod out only by continuous diffeomorphisms. Diffeomorphisms, if you remember, connected to identity. These SL2Z transformations are generated by diffeomorphisms, like Z goes to Z plus 1, right? But they're generated by diffeomorphisms that are not continuously connected to identity. They're discrete diffeomorphisms. So these also should be modded out by, you don't need to add ghosts for this. Okay? Because there's no determinant issue, because they're discrete.
There's no infinitesimal.
Exactly, there's no infinitesimal version. But you do have to mod out by these things. The way to mod out is just by working in a fundamental, fix a gauge. Right? Choose one of the taus up to SL2Z. Okay. So now I will leave this as an exercise for you guys to prove. that up to SL2Z transformations, you can always put tau inside the following fundamental domain. The fundamental domain is obtained by the unit circle, and its intersection with, what was it? Sorry, just firstly there's half here, minus half, and then it goes like this, right? Just a minute, let me get this. I'll just get this straight. Sorry, what am I saying? Yeah, the one we normally use is this one. It's the X, sorry, thank you. It's this guy. Actually, there's a tau goes to 1 by tau if this is this. Okay. You can always use SL2Z transformations to put it in here. What's the general idea? The general idea there is that you can always put it between minus half and half by using the shifts. And there, if the modulus of tau is less than 1, well, then you use tau goes to minus 1 by tau to make the modulus of tau greater than 1. Now, this is not that simple to argue because these things don't commute. That is, suppose the modulus of tau is less than 1 here, and then you put it in the strip, then you do it, you might go out here. You have to then put yourself back here. Okay, and you have to argue that this closes. It's a little exercise you can play around with. Okay, but it's not too hard to convince yourself that you can always put, by using SL2Z transformations, you can always put this in this region. Okay, that every value of tau can, by an SL2Z transformation, be moved into this region. Roughly, it's because you can move to the strip and you can make the modulus greater than 1. That's roughly right. And then you have to do it a few times. Okay, excellent. So, now what we have to do when we were...
This region is also infinitely extended.
Infinitely extended, all the way up.
Yeah, because the imaginary part of tau should be unconstrained.
Right. Right. Now, the next thing I want to do is to take this formula and the formula that we have and interpret it in terms of quantum field theory. Okay, so what is the formula we have? The formula we had was d2 tau over im tau, the whole thing to the power 2 times 1 by eta tau mod squared im tau square root im tau, the whole to the power 24. A very beautiful and simple formula, as you see, right? Okay, so we've got this nice formula here, and I want to interpret this in terms of quantum field theory. So what do I mean? What I mean is, well, you know, all we're doing is one loop string theory. And at one loop, string theory is free. And so you might think that this answer here should have something to do with one loop diagrams over the spectrum of string theory. If you were just doing a free quantum field theory and you wanted to compute the vacuum energy, you would do this one loop graph over, at one loop, you would do the one loop graph over every particle. What is the connection between that and this calculation? That's the question we're going to ask. Is the question clear? Okay? Answering this question will help us get a physical sense for what this formula is doing. And that's why it's important. Okay? So let's start. So suppose I had a particle of mass, of mass m square, and I wanted to compute its vacuum bubble. I wanted to compute this quantity here. Oh, what is it?
In momentum plus ddk over k square plus m square.
Well, it would be ddk over k square plus m square if it was this diagram, because that has one propagator, but a vacuum bubble has 0 propagators. It's the determinant, right?
Oh, right.
Yeah, so this is minus log of k squared plus m square ddk over 2 pi to the power. And maybe a half. We were doing a, I'm not sure how precise we'll be, but if we were doing a proper calculation, we would put a half, because you get square root for a real particle, for a real field. Right? All I'm doing is computing the determinant. You understand where this came from, right? This came from doing path integral d phi exponential of minus of del phi square plus m square phi square by 2, and doing just the free part. So that gives you these logs, 1 log for each momentum. The reason this factor of half is there is because you got square root when you did.
It's the square root of determinant for
Square root of
one
determinant.
field.
Exactly. Okay, excellent. Now let me think for a moment. Is that half really there? Probably not actually, because it's like phi of p, phi star of minus p. Yeah, well, no, but it is there if you do over p and minus p.
For one real field.
Yeah, it's correct. Yeah. Okay, excellent.
For one complex field, the half won't be there.
Won't be there, yes. Excellent. Excellent. Okay. Now this looks like a nice answer, but we want to take this answer and sum it over all of the spectrum of string theory and compare with what we have there. Now, if you take
sum over all the masses.
Sum over all the masses, but when you want to sum inside a log, it's not very nice. So let's try to find a representation of the log that makes doing the sum easier.
Heat kernel.
Exactly, heat kernel, Schwinger, whatever. It's this representation that's always useful. The representation we want to take is logs come from dx by x. Okay, so dx by x e to the power what is it? Dx by x e to the power minus ax.
Just 1 over a.
Right. Dx by x e to the power minus ax basically gives you this. Basically gives you log a. Okay. Let's do the integral from 0 to minus infinity. We need some regulation at 0. But if you do it appropriately regulated, the dependence on a, let's say we put an epsilon. Let's work it out. You put an epsilon here. This quantity here, this quantity here will be well, the easiest way to work it out is this. Let's do it without this.
Or we could do some other regulation, some x raised to power alpha and dd alpha with alpha going to
X raised to the power alpha. We could, but
yeah,
let's not
just
complicate life. Yeah. Okay. If we work this out, this is clearly proportional to a.
This is 1 over a.
This is 1 over a. Thank you. Proportional 1 over a. Okay. Now we want to get an extra factor of so this Exactly. So let's say this is I. Let's say I prime. What we are really interested in is I, which is equal to dx by x e to the power minus ax. Okay. Now the derivative of I with respect to a is I prime.
Yeah, right.
So what can I be such that its derivative is 1 by, well, it has to scale like log a. Okay. And we will not worry about the regulation. It will deal with itself. Okay. So we will, if we want to do this carefully, we should regulate. But right now, naively, we will just use this as the representation for log a.
Yeah, there will be some subleading.
Some stuff, and to make sense of it, we have to regulate.
Yeah.
Okay. We should do all that. We're not being so precise. We're just going to use this for some intuition. And all this can be made very precise, as you know. Okay. So now what is this? In fact, I will change the notation. Instead of calling it this x, I'll call it t to make it look more suggestive. So dt by t. And now I want log of...
There's probably a sign. It should be minus log a, but that won't matter.
It will be minus log a. Let me understand that. This guy was 1 by a.
Yeah, when you hit with dda on the second guy, that will be the minus of the first guy. I mean, del I del a is minus I prime.
Why is it minus I prime?
Because it's exponential as a minus in the
Ah, you're right.
Yeah.
You're right. Let's put a minus here.
Yeah.
You're right.
And in the limit of very small a, the integral should diverge to positive infinity. Therefore.
Excellent. Let's put a minus sign. So we have minus d by dt times e to the power minus t times we want, and let's put a half here because we want that half, and then minus t, and we've got k squared plus m squared.
This is called heat kernel.
Heat kernel, Schwinger, I'm not sure. It's got some name. Okay. 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 Now, of course, we want this, and that's just what this log was. But we have to continue to integrate that business there. So we've got minus half ddk divided by 2 pi to the power k. K is, of course, d is 26, but I'm writing d because it's sort of nicer to write than 26. Okay. Okay. Great. Now, what I'm going to do, what I have to do is now I have to sum over the whole spectrum of string theory. Okay? So what I have to do now is to do this I and sum over I. Now the great thing is that now summing is not tough. Sorry, what I need to do is actually do the product over all of these, right? Because I get one factor of the determinant. Yeah,
for each sector.
Yeah, but no, but actually we'll actually want to do a sum, right? Because this is the log is in the exponent. The determinant I got log because I took exponent. Yeah, so I actually want to do a sum. You understand, right? I mean, I didn't actually do the path integral. I did the path integral and wrote it as e to the power something. So when you take the product of all these e to the power somethings, you're summing the logs. Okay, so we want sum over I. Now, so the sum over I can do here. I have sum over I here. So now what I want is the sum over, and the e to the power minus t k squared can also go out. So I've got dt by t e to the power minus t k squared. So I only need to do the sum over I e to the power minus t m I squared. what was mi square? What was mi square? Well, you know, we have these oscillators, right?
Yeah, but the tachyon we have to exclude by hand.
Well, let's exclude nothing because we'll do it also. At least formally, we should get the answer including the tachyon.
Yeah.
So what was mi squared? Mi squared was was related to the Hamiltonian or oscillator number of the excited state. Okay, so so now let's work in light cone quantization. Okay.
Yeah.
24.
But we also have to count the number of particles at that.
Absolutely. So at any given level, we have to count how many oscillator states have that energy. Okay, and that will tell us how many particles of mass mi squared there were.
So in light cone quantization, we just went like n minus 1.
Okay, but what are we saying? We're saying that this mi square here is effectively then the if we suppose I did this. Suppose I took this. Let's do just the left to start with. What was this 1 over? What was this 1 over eta tau? Eta. Let's just do the left. What was this 1 over eta tau? It was, as you know, trace q to the power L naught.
Yes.
But L naught
Was precisely the mass.
was m square. Let us remember the precise relationship between L naught and m square. Okay, the precise relationship was for the bosonic string closed, where minus 4 by alpha prime m square was equal to 4 minus 4 by alpha prime into n minus 1.
Yeah.
N was the oscillator number. N minus 1 is, in fact, this minus 1 is just the sum of all the 0 point energies inside the etas. Because each 0 point energy, each eta has 0 point energy 1 by 24. Okay? So what am I saying? What I'm trying to do is to show you that this quantity here is precisely L naught for 24 oscillators, up to a normalization which we'll get, is proportional to L naught for 24 oscillators. Because L naught was oscillator number minus 0 point energies. Each oscillator had 0 point energy minus 1 by 24. But there were 24 such oscillators. So total oscillator number minus 1 is L naught. Okay? So this thing here was L naught. So what we see is that, look, let us just compute. So we see that L naught was equal to alpha prime m squared by 4. So summing, what we want? We wanted e to the power minus t summed over all mi squared. Okay? But that is, so I'm going to give you the claim and then you see if you agree with me. That is the same as trace of e to the power minus t, and now I just have to convert what is m squared is 4 L naught, 4 L naught by alpha prime. Is this clear? So this sum over mi squared is very easy to do up to one complication we're going to come to now. The complication has to do with the fact that we have only dealt with the left movers. We also have to deal with the right movers, but you independently specify what the left mover is doing, you independently specify what the right mover is doing, but not.
There's a level matching.
But there's a level matching condition. The level matching condition tells us that L0 and L0 bar are not independent. But let's pretend they were independent and then put the constraint. So then we will get, trace e to the power minus t for L0 bar by alpha prime. That will correctly give us what we want, right? Maybe now we wanted m square, this will give us 2m square. So let's do it with the factor of 2. Because these are going to turn out to be the same. And each of them is related to L0 in this fashion. We want m square, so we can get, we're wording it as half of for alpha prime L0 plus for alpha prime L0 bar. Right? So it's this, provided we can enforce the constraint that L0 is equal to L0 bar. Now how do we enforce that constraint? That's very easy. We enforce it with the delta function. We know that L0 minus L0 bar is an integer because the 0 point energies are the same. They cancel and then they're just oscillators. So all we have to do is to put an e to the power I theta L0 minus L0 bar and do integral d theta divided by 2 pi. If L0 minus L0 bar is an integer, no, what I've done this wrong. That's delta function. Exactly. If it's anything but, if it's an integer, if it's any integer other than 0, we'll get 0 because we're integrating an oscillating function over the circle. So this will click only when this is delta L0 bar. Only works when, this range of integration only works when the difference between L0 and L0 bar is an integer, but it is an integer. Okay, so we put that in by hand. So now, where are we? Somebody who remembers this formula, right? I'm cleaning this up. Okay, excellent. So now we plug this into here. So what we wanted was this, but we've got an efficient formula for this. We've got an efficient formula in terms of trace this, trace that, times that extra quantity. Okay, so our efficient formula now is minus half d k divided by 2 pi to the power k. Then d, thank you, dt divided by t, d theta divided by 2 pi. Okay, e to the power minus t k square. Okay. And then this business, which was trace of e to the power minus 2t by alpha prime plus I theta into L0 e to the power minus 2t by alpha prime minus I theta into L0 bar. All good? Okay. Now, at this stage, we can just do the integral over k. This is a Gaussian integral and will give us 1 over t to the power d by 2.
Yes.
Okay. So we'll get minus half integral dt divided by t square times 1 over t to the power d by 2 minus 2 minus 1. Now I'm going to put in d is 26. Okay, so t to the power square root t to the power 24. Okay, times now let's make the following change of variables. Let us call 2t by alpha prime, let's call that tau 2. And let theta be equal to tau 1. Change of variables in an integral. Now, this quantity is, oh, and we want some 2 pi's. Exactly. This quantity now is q to the power L naught, because we have I tau 1 plus tau 2. The plus becomes minus because I 2 i's. Huh? And then we have, so we have q to the power L0 and q bar to the power L0 bar. The q bar has, remember there was a minus sign because it was minus 2 pi I tau bar. Okay, so it works out nicely. Okay, and so now what do we get? We get minus half. Now there are various factors here. So for instance, we haven't kept pi's and so on. I'm just keeping dependencies. Okay, this t is replaced by im tau because it's tau 2. It's minus half dt d theta divided by im tau. Okay, so this is the same as d2 tau. Im tau, the whole thing squared, 1 over im tau square root to the power 24. And then trace of over oscillators, light cone oscillators, of q to the power tau, q bar to the power tau naught. But that is simply, it's just like, that is simply, our eta to the power 24. Tau eta mod square to the power 24. And so this looks exactly like the formula we wrote down before. Maybe we got a factor of half of whichever.
And there are because this is dt d theta, and you will need d tau bar. So
Yeah. Let's not worry about that. Sounds good. Okay, sounds good. Maybe that's a factor of half. Okay, so let's not worry about it. Okay. However, there is one serious difference. And that serious difference was in the range of integration. Let's go back and ask where our t was integrated over. 0 to infinity?
Epsilon to infinity.
Epsilon to infinity. Where was theta integrated over? 0 to 2 pi, but you know, then we added a 2 pi. Let's say it was integrated from minus pi to pi.
Yeah.
Okay, but then we added an extra 2 pi here. So this tau 1 is integrated from minus half to half.
Yes.
So now what do we have? We have two different answers that look very, very similar. This is field theory and this is string theory. Okay, the answer for field theory is integral over the same integrand, but over here, whereas the answer for string theory is integral over this integrand over a different domain, this quantity. What? The factor of 2 you're saying? No, this is actually a factor of infinity. Because you see, one image of this lies in here, but then there are other images in here. This point in particular is a very singular point.
The t equals 0.
Yeah, and it's very important. I mean, it was very nice that in a domain that was excluded.
even for that also epsilon is excluded.
What?
That point is excluded by that regulation.
By that regulation, but now let's say we've taken the regulation away. You know, right. We're going to talk about many of these things in more detail as we go along. Okay? So, you see, this is very important. Okay? Because provided the answer, see, this guy here, and we're going to analyze this in detail very soon, but this guy here has two possible problems, this function. The behavior at 0 and the behavior at infinity. And we're going to very soon just analyze all of these behaviors. You're going to look at them. Okay? But, so, the field theory answer has possible divergences here and here. But the interpretation of these possible divergences in field theory are totally different from each other. Let's go back and ask, what was this? So, what is this? This point is little t is equal to 0. In fact, this whole line is little t equals 0. And that point was little t equals infinity. Now, what was the origin of t? Up to factors, what we had was e to the power minus t k squared plus m squared. Right? So, if t is very large, we can only possibly get contributions from very small k. Right? Any reasonable k is just killed off in this integral. Only very small k. So, if we get some divergent behavior from very large values of t, that in space-time reflects an IR divergence. So, large T is associated with the IR. Is this clear?
And where the divergence is coming?
No, if there is a divergence. Suppose there is a large contribution. There will be because of the tachyon. Oh. Okay, but there won't be in the superstring. Okay? But so suppose we get some problem at very large values of t, it's clear it's an IR effect. Because only very small values of k can contribute.
It remains in string theory, but string theory regulates the UV divergence.
Exactly. On the other hand, if we went near t equals 0, t is acting like a cutoff on k. At any finite t, no matter how small, k cannot become arbitrarily large. So, t is basically being some sort of cutoff. But then once we do the k integral, the region of small t is associated with the region where large k can propagate without trouble. So, if we get any funny behavior near small t, that is to be associated with funny behavior because of large k in space-time, the UV. So, these are, from the field theory point of view, very different interpretations of the same, okay, very different interpretations. This is associated with the UV, whereas that is associated with the IR. Now, in field theory, we're going to analyze divergences in just a minute. Okay? In field theory, a divergence in the IR is always a physical thing. A divergence in the UV is to be renormalized. Right? That comes from the structure of quantum field theory. Divergence in the UV, we try to make sense of by renormalization. Divergences in the IR are physical. We will see over the next 2 or 3 lectures, you will see this will be the theme of these lectures. IR divergences are a sign of 2 things. Either you're working in the wrong vacuum or you're asking the wrong question. You know, if IR divergences aren't there for fun. When they happen, it's the theory hitting back at you, telling you you're doing something wrong. In QCD, when you get IR divergences, it's a sign that you're scattering particles that don't exist. Gluons. Actually, the theory confines. It's always like that. We will see examples of this. Okay? But UV divergence is sort of different. There's some regulation effect. You change your regulator, you get a different answer and so on.
So just in that context, taking
yes.
your point, what do the divergences in QV
Yeah, so they tell us you're asking again the wrong question. You see, suppose you ask the question, what is the scattering amplitude for two electrons, let's say 2 photons to go to 2 photons. The answer is just 0. Why is that? It is because given such a process, there's always a nearby process in which a nearby soft photon has been emitted, and then another, and then another. So the chance that exactly two photon scattering will emit exactly 2 photons is infinitesimally small. So by asking what is 2 to 2 scattering, you're asking a stupid question, so you're going to get a stupid answer. Okay? People know how to cure this by looking at these inclusive cross sections, right? Because then when you're asking a question that can be measured in an experiment, it's not a stupid question. It has to have an answer. The meter will give you some answer. What is it? But meters cannot distinguish 1 photon and 2 with half momenta that are basically collinear. 1 photon going this way and 2 photons going so it's the usual story, right? If you read Weinberg, the IR divergence story, it's basically because you're asking the wrong question then. That's one example. Okay? There are other examples where you're working around the wrong vacuum. It's usually one of these two things. Either you're asking a bad question or you're working around the wrong vacuum. Okay? Whereas, fine. Now, what happens in string theory? In string theory, as we see, IR is the same as in field theory. Okay? But the UV is just not there. What does this mean? It means that apart from potential IR problems, which may be there because we may be asking the wrong question. In fact, here we know we're asking the wrong question.
Because we are in the wrong vacuum.
Yeah, exactly. We're about a vacuum that's like balanced at the top of a hill. Classically, you can set yourself there. Quantum mechanically, you'll roll. Because fluctuations will set you rolling. Okay, so it's a stupid question we're asking. Working around the wrong vacuum, we're going to get infinity. But for some known IR reason, not because there's some short distance problem in the theory. Once you cure that IR problem, you'll cure it. Okay?
The way we chose this region in string theory,
yes.
we did this flip one.
Yes.
But I can do that again.
Excellent question. Excellent question. So the question goes, look, this business of, let me say, as Anurag said, I do a tau goes to 1 by tau, and this will turn this to this thing. And now this thing includes this point but excludes that point. The real statement is this, that any divergences in string theory can always be interpreted as IR effects. There's always a channel in which to view them, in which they are IR effects. And therefore, if your theory has no problems, it cannot exist. Okay? Once you've done that, you could, as you said, do the modular flip and view it as a UV effect. So the real statement is this, that string theory...
So it's a T-dual statement of that.
Not exactly T-dual, but it's a modular flip on the world sheet. The real statement is string theory can only have UV divergences if it has IR problems.
If it has IR problems.
IR problems, because every divergence can always be viewed, there's always a way of viewing it. It's not the unique way. There's always one way of doing it, so that it's associated with the IR in space-time. And then, if you view it another way, that's a map of that problem. As you see, if this thing has no problem here, then this can have no problem here, because infinity maps to 0. Okay? So that's the real statement.
You were saying in QFT these are
completely different phenomena.
different things.
Exactly. In string theory, what happens in the IR is controls what happens in the UV. So, if you have problems in the UV, you might, if there's a way of, but that's only because you had problems in the IR.
That's a genuine problem.
Yeah, exactly. Once you get rid of that problem, you will also not have problems in the UV, like in the superstring. Okay? Excellent. So, now let's keep going. Now that we understand this.
So is it in some sense an UV-IR duality?
Yes, it's sort of UV-IR duality in the on the world sheet of the string. Or more precisely, it's what some people sometimes call channel duality.
Some long string, short string.
It's this, that you see, if you cut a string, you've got a string world sheet, and you've got two ways of cutting it. What is space and what is time, for instance. Okay, you cut one way. So suppose you've got this. Suppose you've got this torus. Now you can view this torus as this string going around like that.
Yeah, or that string.
Yeah, maybe it's better to draw it like this.
Yeah.
Okay, you can view it as this string propagating time like this, or this string propagating time like this. Now let's make the torus a little asymmetric.
Either a very short string going a long way or a very long string going a short way.
Exactly. Now a long string going a short way is a UV thing, because it's going over a very short distance. But a short string going a long way is an IR thing. It's going very long distance. Okay, that's roughly the sense of it. That there are different ways of cutting the same world sheet that make it look different. It's a bit, yeah, it's more precise here, but roughly that's the sense of it. Okay, excellent. So let's keep going. Now that we've got sort of assured that the only problem that we could have here is in the IR, next question we're going to ask ourselves, so do we have a problem in the IR? Okay, so do we have a problem in the IR? Well, let's just see. We've got an answer, so let's just look at it. So we've got d2 tau divided by im tau, the whole thing square, times 1 over eta tau mod square square root im tau to the power 24. Now, what we're interested in is what happens at very large imaginary values of tau. Okay, so remember what we had was q was equal to e to the power 2 pi I tau. We're looking at very large imaginary values of tau, so let's set tau is equal to it. So q is equal to e to the power minus 2 pi t. Okay, and we're looking at very large values of t. So any positive power of q here is utterly well behaved. However, negative powers of q are bad news.
Yeah, which is what we have.
Exactly. So now all we have to do is to take this business and expand it in powers of q. Do you have a class, Rishi?
No, I just want to
Yeah. Yeah, of course.
It's exponential versus some polynomial.
Yeah, but the polynomial is utterly unimportant. It's just what the exponents are. Exactly. So now let's look at this eta. So firstly, remember that this was q to the power minus 1 by 24. That was on top, because we had, when we were doing a partition function, we had q to the power q to the power L0. L0 had the minus 1 by 24. So downstairs we had 1 over q to the power 24, and then product over n, 1 minus q to the power n. So this is what this eta was. Right? So now if we look at what this is, so all these q's are small, so we just want to Taylor expand. So the leading term comes from here, it's q to the power minus 1 by 24. 24 powers of that. So q bar to the power minus 1. Q went like e to the power minus 2 pi t. q bar goes like e to the power minus q by 2 pi t. So this goes like e to the power. So let me put tau. Yeah, let me put tau is equal to it by 2 pi. So I don't have to keep. Okay, so this goes like e to the power plus 2t. Okay, and clearly the integral over it is going to diverge. Now, what is the source of that divergence? Where did this come from? This came from the ground state of the oscillators. That was the term that gave us the divergence. What was the ground state of the oscillators? It was the tachyon. So if you go back to the field theory part and see, where is this divergence coming from? It's coming from one particle, namely the tachyon. Okay? So it's definitely diverging because this is e to the power 2 pi t, 2t, but the divergence is completely due to the tachyon. Now let's continue our Taylor expansion. Okay? What we're going to get is q bar to the power minus 1, that's what we had here, and then we have all these factors downstairs. So we have to Taylor expand in this q. The leading term will be q.
Yes.
So 1 plus 24q times 1 plus 24q, and you know we have to do level matching.
Yeah.
We've been ignoring this integral over the imaginary part of tau, but as the field theory derivation showed us, it wasn't completely ignorable. It only gave us contributions from states with q equals q bar.
So the n and from the left and right sector have to be taken at the same level.
Exactly. So we'll get q bar to the power minus 1. So then we have 1, and then we'll have
Just
plus
1.
20,
Will be 1.
24 squared times q bar.
Yes.
Okay, this cancels this. So we have 24 square.
And they all
And now the
denominator.
powers start mattering.
Yeah.
Okay, but the powers are good because it's like t to some large power 13.
Yes.
That's nice and integrable at t equals infinity. What are the interpretation of these states? What are these states that we just looked at?
Massless and massive string states.
Well, this one was exactly the massless
string states.
massless string states. Why did we get 24 square? Because of the polarizations. Remember, it's a symmetric, it's a tensor.
Yeah.
You can break it up into symmetric, anti-symmetric, and trace, but that doesn't matter because you're getting contribution from all. So it's just an arbitrary tensor, which is 24 times 24 dimensional tensor. So how many particles were there? Well, 24 square.
Yes.
Okay? And they were all massless. And the fact that they were massless gives you some of this t business. You can actually check from the field theory that you get the same power of t from massless fields. It's just the ddk integral. Okay? And so this is now not a divergence. It's a perfectly civilized behavior. And it's coming from the massless states. Of course, if you expand one more power, then you
will
get
be exponentially suppressed.
exponential suppression. So even the power law becomes unimportant. And it just gets better and better. All we're seeing is that things that are, there was a delicate question whether the massless fields would be IR divergent or not. For this purpose, they're not. You know, it's generally true that IR divergences get better and better in high-end dimensions. Here we're in very high dimension. Okay? And then massive fields are never IR divergent. So every time, once we go to the higher oscillators, it'll be completely clear. Okay? Good. So already this torus amplitude has taught us quite a lot. Okay? It's taught us, we've already learned quite a lot. And actually it's sort of nice that we're working with the, with the bosonic string for this purpose, because in the superstring when we do the same computation we would just get 0. Can anyone interpret why we'd get 0?
Because of Bose-Fermi cancellation.
Exactly, because this boson one loop will cancel the fermion one loop.
Because of space-time supersymmetry.
Because of space-time supersymmetry, exactly right. Okay, so some of what we're seeing here will get obscured by that fact. Of course, we won't get 0 once we put vertex operators. So the essential physics is still there, but it's a bit easier actually to see what's going on here in the bosonic string. Okay, you can also work in one of these. We should come back to the heterotic string at some point. We should all. There are these. I can't remember. Did we discuss the non-supersymmetric heterotic strings? I think not. We didn't discuss the off-diagonal, the strange modular invariants, did we? I will come back to it. We'll come back to it. The heterotic string. There is a nice. In the heterotic string, it's possible to build tachyon-free, but non-supersymmetric heterotic strings.
Non-supersymmetric means no space-time supersymmetry.
No space-time supersymmetry, exactly. And these are sort of nice objects because they don't have the tachyon, so they won't have this IR divergence. But they don't have supersymmetry, so one loop things won't cancel. So they're not nice from the point of view of physics. Not nice from the point of view of physics because then the one loop vacuum amplitude will generate a one loop cosmological constant, which will start curving space-time, will tell us that at long distances what we really thought we were in flat space, we wouldn't be. Okay, it's not nice for phenomenology and so on, but it's nice as a testing ground for certain ideas. So that would be an example in which, if we worked it out for that heterotic string, as at some point we will, we'll see that we'll get an entirely finite one loop partition function. Completely finite, something that's a number. A computable one loop vacuum energy. This, by the way, is a very nice thing. You see, in quantum field theory, things like vacuum energies are essentially uncomputable. In string theory, they shouldn't be uncomputable because vacuum energy couples to gravity. And it is computable, as we've tried to see. Okay, the only possible problems are IR problems. When you have no IR problems, you have a finite answer. Okay, all good? Fine. Now I think we're going to start working with the open string, but it's different enough that let's do it next time.